Hi guys, welcome back to this new MCAT physics series where we're going to talk about fluid. So fluid is actually one of my favorite physics topics since I'm extremely interested in the physiology of respiratory and circulatory systems. So as you can see, there are 3 tutorials. In this very first video, we're going to clear some basic concepts about fluid, and then we're going to move on to hydrostatics, which is the study of fluid that are not in motion, aka being static. And then in our last video, we're going to study the hydrodynamics, which is the study of fluids that are in motion. All right, so let's jump into the basics of fluid. Okay, so first off, what is fluid? So fluid is basically any substance that can change its shape correspond to that of the container that it is put into, right? So according to definition, fluid really includes both liquid and gas, okay? Not just liquid, but also gas, right? Okay, so now let's talk about the density of fluid. So what is density? Easy peasy, right? Density is the measurement of mass over the volume. All right, so the SI unit for mass is kilogram, and then for volume is meter cubed, right? So that will be the SI unit for density, and then it's symbolized by the Greek letter rho. Not to confuse that with the capital letter P, which presents pressure. All right, so the liquids, the difference of liquids density versus the gases density is that the liquid is usually incompressible, which means that if you have some liquid, and then if you want to press it down the liquid, it has to be leaked out or get spilled out in some way, right? Whereas the gas is really compressible. Okay, so you can think of the different air pressure at different elevations, different latitudes, right? The magnitude of the air pressure will be different if you are at sea level versus on top of a huge mountain, right? All right. Okay, so another thing I would like you to know is the density of water. So the density of water, let's make it more curvy. Okay, so the density of water on MCAT at sea level, 1 atm, 4 degrees Celsius, is 1,000 kilogram per meter cubed, right? Okay, and then that equals to 1 kilogram per liter, right? And then that also equals to 1 gram per milliliter, or 1 gram per centimeter cubed, right? So basically, these are different unit expressions that are describing the same thing, which is the density of water, right? Okay, so what about seawater? So obviously, it's more dense than pure water, right? So the ocean, we can put a 1.03 gram per milliliter, which is slightly more dense than pure water. But the liquid mercury is way more dense than water at 13.5 gram per milliliter. Okay, all right. So now let's talk about specific gravity. So what is a specific gravity? So specific gravity is basically the density of anything. It can be solid stuff or liquid, right? Or even gas, right? Divided by the density of water. Okay, and then since it's a ratio, so this thing is really unitless. Okay, but what you want to pay attention is the unit you use here for density of water should align with the unit here, right? You don't want to use SI unit here, but here the density you would use like gram per milliliter. You don't want to use different units, right? Okay, so let's give a couple examples. So what's the specific gravity of ocean water? So like we know the density of ocean water is 1.03 gram per milliliter divided by the density of water, which is 1 gram per milliliter. That gives 1.03 specific gravity of ocean water, right? What about mercury? Mercury is 13.5 gram per milliliter divided by 1 gram per milliliter. So the specific gravity of liquid mercury is 13.5. Right? Okay, so what about some solid stuff that has a density of, let's say, 800 kilogram per meter cubed? Okay, so to calculate the specific density of this thing, we want to use the water's density, the SI unit, right? Which aligns the two units. That give us 0.8. Okay, so this thing is obviously less dense than water, right? Okay, perfect. So now let's move on to pressure. Okay, so what is pressure? As we discussed in the force, torque, work, and energy and power series, force is really pressure is really force over some area, right? And then the SI unit for force is Newton, right? It's also kg times m per second squared, right? And then the SI unit for area is meter squared, right? So that gives you Pascal, right? Okay, and then besides Pascal, we also see some other units of pressure, like milliliters of mercury, right? Or we see pounds per square inch, like PSI, right? And then also torr, okay? So MCAT would really ask you to do the conversions of these units, but what you want to know is the air pressure, the atmosphere pressure at sea level, okay? Okay. So the most famous one is 1 ATM, right? And then that equals to how many Pascal? It's 10 to the fifth Pascal, right? It's technically 1 times 1.01, but we on MCAT we can just use 10 to the fifth. Ignore the 0.1 part. Okay, and then that equals to 100 K Pascal, right? And then also that equals to 760 milliliter of mercury, and that equals to 760 torr. Okay, awesome. So these are the values you want to know, you want to memorize, okay? All right, so there are also 3 different pressure concepts I want to discuss. The first one being hydrostatic pressure. Okay, so what is a hydrostatic pressure? So let's imagine you have a system where there's water or any liquid in there, right? And there's an object. There's an object sunk to the bottom. So this object is really experiencing some force exerted by the liquid surrounds it, right? So to quantify the hydrostatic pressure, the equation is P, right? Capital letter P equals to the density of this liquid times the gravitational acceleration times the h, which is the depth of the submission, right? The depth of submission. Okay, so this will give you a value in unit of Pascal, right? Since it's a sort of pressure. Okay. The second one I want to discuss is absolute pressure. So let's use the same system, the same container, okay? Okay, the same object here. So the absolute pressure is actually the pressure of hydrostatic plus the pressure, the atmosphere pressure. Okay, so in the first case, we take this hydrostatic pressure into account, but not the air pressure that the same object is experiencing, right? So the air pressure is here, right? So this object is really experiencing two different pressures, right? One being the hydrostatic pressure from the water or other liquid or any other liquid, and the pressure from the atmosphere, right? Okay, so let's calculate the absolute pressure of this system. Okay, let's say the submersion is 10 meter. Okay, so the hydrostatic pressure will be, and then let's imagine that's just water. Okay, so the density of water is 1,000 kilogram per meter cubed times the gravitational acceleration, which is 10 meter per square second, and then the submersion is 10 meters in depth, right? And then that will give us 10 to the 5th Pascal, which equals to 1 ATM. Okay, and then let's imagine this thing is at sea level. So the ATM it experiences equals to 1 ATM at sea level, right? So the total absolute pressure the whole system experiences is 2 ATM, right? Okay, perfect. So there's a third pressure I want to discuss. Okay, so the third pressure I want to discuss is called gauge pressure. Okay, so gauge pressure basically equals to the absolute pressure minus the pressure from atmosphere. Okay, so as you can see, hydrostatic pressure is basically a kind of gauge pressure, right? And then the reason we bring in the gauge pressure, why we calculate gauge pressure, is because most objects are at the same elevation levels, a similar latitude, right? So that we don't need to take the atmosphere pressure into account, since they're experiencing, all the objects are experiencing very similar atmosphere pressure. So that's why most of the time in real life we would just have a calculation of the gauge pressure. Okay, all right. So now let's draw a graph to link the ideas. So here on the x-axis is the depth of the submersion, and then on the y-axis is the absolute pressure. Okay, so the graph is as the depth of submersion increases, our absolute pressure, of course, increases, right? But we also see that here, this part is really the pressure from the atmosphere, whereas this part is the gauge pressure. Okay, all right, so that wraps up the first part of this video series about the basics of fluids. I hope that's helpful. And then in our next video, we're going to move on to hydrostatic statics.